Hello everyone. In previous lecture we studied about drift motion, drift current, drift velocity and mobility, and also seen there how its work and how we use in a different kind of applications. Today we discuss about the current density, electric field and mobility. Today we also discuss about the relation between the current density with conductivity. First topic is the current density. Current density is a physical quantity used in a field of electromagnetism to describe the amount of the electric current flowing through the unit cross section area in a material. In short, we can say that total electric amount which pass through the cross section area of the material known as a current density, represented by the symbol J, and is typically measured in a unit of ampere per square meter in a SI system. Mathematically, current density J is defined as a ratio of the electric current I passing through the certain area A. So, finally, we got the formula J is equal to I by A, where J is the current density, I is the electric current and A is the cross section area through which the current is flowing. Current density takes into account the concentration of the electric current within a given area. In situation where the current is distributed universally across a material, the current density helps to provide more detailed understanding of how the current is distributed spatially. For example, imagine you have a wire with a certain amount of electric current flowing through it. If you were to measure the current on a specific point, you would get the total current passing through that point. However, if you want to understand how concentrated the current is within the wire, you would use the concept of current density. A higher current density indicates more concentrated flow of the current within a given area, while a lower current density indicates the more separate out current. Current density provides a way to describe the distribution of electric current within a material considering the ratio of current to cross section area. Is valuable concept in understanding the behavior of electric current in a various material and devices. Now, second one is the conductivity. We also known as the electric conductivity is a fundamental property of the material that describes how well they can conduct electric current. It is a measure of the material ability to allow the flow of electric charges, typically electrons, in response to an applied electric field. Material with high conductivity allow electric charges to flow easily, while materials with a low conductivity impede the flow of electric charges. Conductivity is denoted by the symbol sigma and is usually measured in a unit of Siemens per meter in the international system unit. The inverse of the conductivity is the resistivity, which is measured how strongly material resist and flow of electric current. Mathematically, conductivity and resistivity are related by the following equation: sigma is equal to 1 by rho, where rho is the charge density. Conductivity depends on the various factors including the type of material, temperature, impurity present in a journal. Metals tend to the high conductivity measure there have large number of free electrons that can move easily through the material's atomic lattice. Insulators have low conductivity because they have very few free electrons available for conducting electric current. Semiconductors have intimated conductivity and their conductivity can be significantly altered by the factor like temperature or doping with the impurities. For the example, we use the copper metal known as the high conductivity and the commonly used the electric wiring. On the other hand, material like rubber or plastic are insulator with very low conductivity, making them suitable for insulating purpose in an electrical system. Conductivity play the crucial role in a various applications including electronics, power transmission, telecommunication and the material science. It determines how efficient material can carry and transmit electric signal and power. Now our next topic is the electric field. So, electric field is the fundamental concept of the physics, particularly in the field of electromagnetics. It is used to describe in an influence that electric charges exert on other charges within their vicinity. Electric charges create electric field in the space around them and these fields can interact with the other charges, causing them to experience force and potentially move. Here, background of the key points related to the electric field. We can say that if any charged particle have present in a point, then around them they feel the some forces. That force we can say the electric field. Definition of the electric field. An electric field E is the particular point in a space is a vector quantity that represent the force per unit positive charge that a test charges would experience if placed at the point. Mathematically, we can represent it E is equal to F divided by Q. This is the formula for the electric field, where E is the electric field vector, F is the force experienced by the test charge, Q is the magnitude of the charge. Second one is the direction. The electric field point into the direction that a positive charge would be moved when placed in a field. For a negative charge, the direction of the electric field is the opposite of that the force would experience. Next one is the unit. The SI unit of the electric field is a volt per meter. Electric field lines. Electric field lines are often used to visualize electric field. These lines radiate outward for the positive charges and transmit at the negative charges. The density of these lines indicate the strength of the field. Closer lines represent stronger fields. Next point is the superposition principle in a case of the electric field. The electric field obeys the principle of the superposition, which means that the total electric field at a point due to multiple charges in the vector sum of the individual electric field from each charge. Under this topic electric field, we should know also about the inverse square law. Inverse square law is similar to the gravity. The strength of the electric field decreases with the square of distance from the source charges. Mathematically, the magnitude of the electric field due to point charge q and distance r is given by E is equal to q into K divided by R square, where K is the Coulomb constant. In short, the electric field is described by the charge and magnitude of the charge. Suppose that there are the two charges, first one is the Q1, second one is the Q2. So, their magnitude is the Q1 into Q2 and the total electric field is E is equal to Q1 into Q2 divided by the R square, where R is the distance between both charges. Next, electric field and work. Moving a positive charge within an electric field required or release energy due to work done by the against the electric field. The work done W is moving the charge Q between 2 points with the potential difference V is given by. This is the relation between the work and the charge. W is equal to Q into V, where V is the potential difference between them. The electric field is the fundamental concept of the understanding how electric charges interact and how electric phenomena such as the behavior of the charges in a circuit is the functioning of the electronic devices occurs. Now is the conductivity and mobility. Conductivity and mobility denoted by the sigma and mu are the related concepts that describe different aspects of the how charges move in the material and response to the electric field. That relationship between the conductivity and mobility involves the concentration of the charge carriers in a material. Relate the conductivity and mobility in term of the mathematical form. Definition of the continuity is the measure of the how well its material can conduct electric current. It takes into account the both concentration of the charge carrier, that carriers is the electrons or the ion, and their mobility. Mathematically, conductivity is represented by in this equation. The equation is the sigma is equal to N, Q and mu, where sigma is the conductivity, N denotes the number of density of the charge carriers and Q is the charge of the charge carriers. Mu is represent the mobility of the charge carriers. Second one is the mobility. Mobility refers to the ease with which charge carriers can move through the material in response to an electric field. It is the measure of the average velocity of the charge carriers per unit electric field. Mobility depends on the factors such as the charge and carriers, the electric scattering mechanism with the materials, and the influence of the external condition like temperature. Both relationships we can also understand by different phenomena like higher mobility, higher conductivity. Generally, material with a higher charge carriers mobility will have higher conductivity. This is because higher mobility means that charge carriers can move more easily in response to an electric field, resulting in a higher overall current flow. We also talked about earlier how can understand the relation between the mobility and conductivity. In a second term, we can also understand by this concept higher carrier concentration and higher conductivity. Conductivity is also directly proportional to the concentration of the charge carriers. Material with a higher density of the charge carriers will have higher conductivity, as there are more carriers available to contribute to the current. Next one is the combined effect. The product of the charge carriers concentration and mobility determine the conductivity of the material. Materials with a high concentration of the mobile charge carriers will have higher conductivity conductivities provided the charge carriers have reasonable mobility. The conductivity and mobility are related through the charge carrier concentration and their ability to move in a response to the electric field. Material with a high mobility and high charge carriers concentration tend to exhibit higher conductivity, making them better conductor of electric. To prove the relationship between the conductivity sigma and mobility mu, we can use some mathematical form. Using the mathematical form, we are compare both equation and prove the one another equation. By comparing the expression for the current density and conductivity, we establish the relationship between the mobility and current density. Like we know that about sigma conductivity described by this equation, sigma is equal to nq mu, and current density is described by the equation J is equal to nqvd. We know that current density is the J related to the electric field E and mobility mu. Both equation we combine, then we get the J is equal to nqe mu. Comparing this equation with the express the conductivity sigma, and we see that, and we can also say that putting the value of the nq mu, which is the sigma, that is put on the given equation, then we get the equation J is equal to sigma E. This relationship indicate that current density J is the directly proportional to the electric field E and conductivity sigma. This relationship hold for a material with a uniform charge carriers concentration and under the condition where the mobility mu remains constant. The relationship between the conductivity and mobility is established through the concentration between the current density, charge carrier concentration, mobility and electric field. Conductivity is a measure how current density responds to electric field, and mobility play the very crucial role to determine how easily charge move in a response to that fields. Next, our topic is the conductivity in a semiconductors. In a semiconductors, conductivity plays a crucial role in determining how these materials conduct electric current. Unlike metal with a high conductivity or an insulator with low conductivity, semiconductors exhibit intermediate conductivity that can be highly influenced by external factors. Here describe the conductivity in a semiconductors. There are some different type of the semiconductor. First one is the intrinsic semiconductor, second one is extrinsic semiconductor. Extrinsic have the p type and n type semiconductor. In all semiconductor we have different conductivity. Let's start the describing the conductivity of intrinsic semiconductor materials. Intrinsic semiconductors are pure semiconductor material with no intentionally impurities added. Their conductivity arises primarily from the movement of the charge carriers, which are the electrons and holes created due to thermal excitations. At absolute zero temperature, intrinsic semiconductors have very low conductivity since there are few available charge carriers. At a temperature increases, more electrons gain sufficient energy to move from the valence band to the conduction band. Valence band is also known as the filled energy level, and conduction band is also known as the unfilled energy level. Creating charge carriers then can be contributed to electric conductivity. We know that valence band, also known as the filled energy level, and conduction belt, also known as the unfilled energy level. The relationship between the charge carrier concentration and temperature in intrinsic semiconductors follows the exponential relationship known as the intrinsic carrier concentration equation. That equation is presented in a mathematical form, which is the Ni is equal to A t raised to the power 3 by 2 E minus e raised to the power minus Eg divided by 2 kBt, where Ni is the intrinsic carrier concentration, A is the constant, T is the temperature which is in a Kelvin, Eg is the energy band gap, Kb is the Boltzmann constant. Doping an extrinsic semiconductor to enhance the conductivity of the semiconductor. For practical application, intentionally doping is performed. Doping involves introducing the impurity into the semiconductor crystal lattice. These impurities are two types. First is the N type of doping, second one is the P type doping. Introducing the atom with extra electron donor atoms create an excess of the negative charge carriers. This added electron significantly contributed to conductivity. N-type conductivity is characterized by the high electron concentration and low hole concentration. Second one is the P-type doping. Introducing atoms with favor electrons creates excess of positive charge carriers. These holes become the predominated charge carriers and contributed to the conductivity. P-type conductivity is characterized by high hole concentration and low electron concentration. Conductivity and mobility in extrinsic semiconductors. In extrinsic semiconductor, conductivity is strongly influenced by mobility of the charge carriers. Mobility represents how fast charge carriers can move in a response to an electric field. It is affected factor like impurity scattering, crystal structure and temperature. Conductivity in a extrinsic semiconductor is given by this equation. This mathematical equation, which is a sigma is equal to nq mu n plus pq mu p, where n is the electron concentration, p is the hole concentration, q is the elementary charges, mu n is the mobility of the negative charge carriers and mu p is the mobility of the p charge carriers. Conductivity in a semiconductor is a complex due to the interplay the intrinsic and extrinsic factors. The ability to control and tailor the conductivity through doping makes semiconductors highly versatile for the application in electronic devices such as the transistor, diode and integrated circuits. Current density, conductivity and electric field are interrelated concepts in electromagnetism that find the wide range of application various fields. Now, we already discussed about the current density, conductivity, electric field, and also we studied about the relationship between the conductivity and mobility and conductivity and semiconductor materials. Now, we see the how can use in a different field. They have the many more applications in different field like electric wiring and power transmission. Current density J is the electric wiring and current density in a critical factor to ensure that wire can be handle the current without overheating. Choosing this appropriate wire gauge ensure that the current density remains within a safe limits. Conductivity rho. High conductivity material like copper and aluminum are used in electric wiring due to their ability to efficient transmission of the electricity over the long distance with the minimal energy loss. Electric field. Understand the electric field distribution along power transmission line helps engineers design system that maintain stable voltage level and prevent power losses. Now, in the field of the semiconductor devices, current density plays the important role. In a semiconductor material device like transistor, the movement of the charge carriers between the different regions is the manipulated, the control the device and behaviors. Conductivity. The conductivity of the semiconductors material affect their performance in electronic components. Doping with the specific impurities can be modify conductivity for desired functionality. Electric field. Electric field are the crucial in a semiconductor device like diode and transistors, where they influence the behavior of charge carriers and control the flow of the current. Third one is the electrochemical process. The current density in electroplating and other electrochemical process controlling the current density is the essential to the achieve uniform and controlled deposition of the material. Conductivity. Electrodes used in electrochemical cells or batteries often have their conductivity optimized to enhance an efficiency of charge transfer. Electric field. Electric field influence ion migration and electrode reaction the electrochemical system, affecting process such as a battery charging and corrosion. In a medical application field, the current density plays a very important role, like in a medical devices like defibrillators and neuromodulation devices. Understanding current density distribution is the crucial to avoid tissue damage and ensure effective treatment. Conductivity is the also play very important role in a field of medical. Biological tissues have varying conductivities which are taken into account of the medical imaging technique like the impedance tomography. Electric field. Electric field are the used in the technique like the electroporation, where temporary pores are created in the cell membranes for the drug delivery or the genetic manipulations. Electromagnetic compatibility (EMC). In that field, current density play the very important role. Like high current densities can lead to the electromagnetic interference (EMI) in electronic system. Managing current path and distributing help the reduce EMI issues. Conductivity. Conductive materials like shield and grounding system are used to prevent unwanted electromagnetic radiation and protect sensitive electronics. Electric field in EMC studied help assess how electronic devices and system might be affected by or affect external electromagnetic fields. These are just a few examples of how current density, conductivity and electronic field concepts are applied in a various fields. Their understanding and the manipulation are the essential for the designing and optimizing technologies that rely on the behavior of the electric charges and electromagnetic phenomena. So, today we conclude all topic here, and in the next lecture we discuss about the diffusion current. What is the diffusion current, how its work and where we used in diffusion current in a various field. Thank you.